In this lecture, we're going to continue looking at univariate series, but in this case, we're going to look at univariate time series. So the idea here is that we have a series of one feature, one vector of values, but there is a relation between each value and the next because they are in a given order due to the time they occurred. So we're going to look at mortality data and infection with COVID-19, infection, hospitalization, death, and so on. We're going to compare these time series, look at moving averages and how to visualize the time series, and also look at correlations, correlations between series in cross correlation, and also of a time series with itself. We're going to see what use there can be for that. So first, this concept of a time series. We saw in the previous lecture a data series that had heights for different people, where the ordering of those values was irrelevant because each value corresponded to a different person. So actually we even reordered the series to get the cumulative distribution and that kind of manipulation. With the time series, the order matters because we obtained these values in sequence from some set of temporal events. We are looking at univariate time series because we are looking only at one feature. This is common, for example, if you are using a stock index or something like birth rate, something like that. There are cases of multivariate time series where at each instant you have a set of values, several features that you need to consider together. For example, if you are examining weather, you may have temperature, pressure, humidity, and so on, and you may have to look at all of these values at each instant together to get an idea of what the weather is like at that moment. So even though we're going to look at several features, we're going to do that one at a time. So we have mortality, COVID mortality, infections, and so forth. We're going to compare the different series, but we will be handling them as different time series. So let's start with this yearly mortality data. Actually, it's yearly. We have because it's organized in years, but we have data for each day. So in this case, in this file, we have each column corresponds to a year from 2009 to 2020, and each row corresponds to a day from May 2nd to September 12th. So we can think of this as a set of time series, each corresponding to a year, but they are synchronized by the day. So we can load this data. This is the format of the file, so you can load it again with this function from NumPy, load txt. If you load this file, you have a two-dimensional matrix with your data. The array object in NumPy has this shape attribute that tells you how many elements it has in each direction. So the first axis, the first direction, is the rows, and this has 134 rows because these are the number of days between these two dates. And you have 12 columns because of the 12 years from 2009 to 2020, including both of these extremes. So this is the shape of the matrix, and it's generally a good idea if you're dealing with data. The first time you deal with some set of data, it's a good idea to check this to make sure you know what is in the rows, what is in the columns, and if the size matches your expectations. So to take a quick look at the data, we can import pyplot, the same thing as we did before. This is just a quirk of mine. I like using the Seaborn style instead of the default, but this is optional. If you omit this, you just get slightly different plots, but the information is the same. And then you can just plot the matrix. So when you send a two-dimensional matrix to plot will assume that each column is a different data series. So it will represent each column with a line of a different color. And so we have all 12 years, the mortality for all 12 years represented here. Now we can add a legend to put all the different years from 2009 to 2020, and we can add here, send as argument to the legend method in plot a list of strings with all the years. And this is how an easy way of building this list using list comprehension. So in Python, list comprehension, I'm not sure if you covered this before, but you can create a list with this syntax. You use the square brackets at the beginning and the end, and then you type in some expression that can be evaluated in this context. Then you do a loop for some variable in some iterable. Optionally, you can add a condition, and then only those cases in this loop that meet the condition will be added to the list. So in this case, our expression is converting the year to a string. So year is a number. And we are going to do this for all year numbers in this range. So starting from 2009 and ending before 2021. So remember that range in Python produces an iterator that starts on the first argument, or 0 if you omit this first argument, and then stops just before the last one because it gives you that number of items if you omit the first argument here. So if you want from 2009 through 2020, you put one more there, 2021. This will produce all these numbers in turn, and this expression will be added to the list, which is the conversion to a string. So this way we create this legend here, the list of strings for the legend. You can, if you want, instead of using list comprehensions, this is the equivalent of doing it like this. So you start with some list with the empty list, and then for each year you append the conversion to a string. The thing is that with list comprehension, it's often easier to read the code because you immediately understand what we're doing here, instead of having to read several lines and cross-referencing the variables and so on to figure out what's happening. So in many cases, list comprehension actually makes the code cleaner and it's a lot more practical. So another thing that we can see here in this plot is that it's a bit square. It's a bit scrunched here on the sides. We could make it wider because we have lots of points along the x-axis. You can do this with there's a typo here. So you have a fixed size argument on figure when you create a new figure, and you can add the dimensions, width and height in inches to your plot. Now the inches are only relevant when if you save the plot and you specify the number of dots per inches. But abstracting from there, you can use this to set the aspect ratio of your figure. Now, usually so far we did not use the figure here, because when you run a cell with a plot, all the plots inside the cell will be put in the same figure, but when the cell finishes running, Jupyter will capture the figure, show you the figure and clean it from memory. So in the following cell, you'll always start with a new figure for your plot. So in general, you don't need to use the figure function from pyplot. But if you want to set the aspect ratio and or some other properties, then you can use this function. So this gives us a nicer plot because now the shape is a bit more convenient. There's still, this is still a bit confusing. So we saw last week that joining with lines the heights of the different people does not make sense because they are not related. In this case, it makes sense because it's a time series, so you can connect the dots with lines to get a notion of how things are progressing. However, if you have too many lines, then it's hard to see anything. So we can try to simplify the plot a bit by showing the whole data set with dots. So each year is just a set of dots. And then we represent as a line the mean value of mortality for each year. So we average for that day, sorry, not for each year, but for each day. So for the value here is the average over all the years for any given day. This is easy to do because NumPy has this mean function that we can use with a one-dimensional array, but we can also use with two-dimensional arrays or three-dimensional arrays, n-dimensional arrays, by specifying along which axis the mean is computed. So remember, the first axis in a two-dimensional array is the rows. The second axis, which is axis of index 1, is the columns. So axis 0 is rows, axis 1 is columns. If we compute the mean in the direction of the columns, then we'll get an array that has as many elements as the rows in our matrix, and each element is the mean of that row, so in the direction of the columns. Since the rows here are the days, we are computing the mean over all the years for each day. Day 0, day 1, so forth. And so when we plot this, we have this line that is very hard to see, but it's there between all these points. So this improves a bit our graph. Now we can add to the list of labels for the legend the mean here at the end, but it's still a bit confusing because of the way this is represented. So we can improve things a bit. We can change the color for the mean to make it more visible, and we can make the dots transparent, a bit transparent, so they are not as they don't cause that much confusion. So this gives us an idea of the dispersion of mortality, of daily mortality over the different years, and where the mean tends to be. So you see it's a bit higher here in the beginning, and then goes a bit lower as we go in the summer. There are some peaks there. But remember, this is not a full year. This is only between early May and beginning of September. By the way, I chose these dates because they correspond to the dates I have for the COVID-19, but you can do this if you go to the site. You can get the data for the whole year. We can also improve a bit here the legend, because this way it starts overlapping our data. So we can use this additional argument, which is the number of columns in the legend. So we put it in 3 columns, and now it's more rectangular and gets put there in a different corner. You can also specify yourself the corner or leave it automatically. If you check the documentations, there are lots of options for these functions. Okay, so how does this year 2020 compare to the other years? We can subtract the mean of all other years from the last one, the current one, and get an idea of the excess mortality that we have. So 0 is here. In some days we have less death than on average over the past 12 years, but we have some peaks. We can see some peaks here. And the way to do this operation is easy. We just index the last column of our mortality matrix. So this is all the rows, and the column, the last column, -1, we are indexing from the end. And then we subtract the mean computed in the direction of the column. So this is the mean for each row, but using only the previous years. So here we are using all the rows, but only the columns up to the last one. So basically we are comparing 2020 not to the mean over all the years, but to the mean of the previous 10 years. So this shows us excess mortality, but we can see that since these are daily values, they vary a lot from one day to the next, and we can try to smooth things out a bit. For that, we can do a moving average. So in this case, this is a central moving average, because it averages for each point, averages the values around it. So we select a radius, for example 3, and we consider for each point the point, 3 points before and 3 points after. So basically, we're always using a window with an odd number of points because we are adding that radius to the left and the right. This is a bit different from what usually is done in finance, for example, because typically a moving average in those cases tends to be the last n points. So for each point we are only looking at the previous ones and not the ones in front also. So we're going to do this central, I'm going to do this central moving average here, and I'll leave the other one as an exercise for you. So here what we do is we receive a set of values. This is a one-dimensional array, and the radius is the number of elements we're going to move to the left and the right to create that window over which we're going to average. So we're going to start by creating a new set of x values, because if we have a set of points and we compute a moving average by going, for example, 3 to the left and 3 to the right, we cannot do that for the first point because we have nothing to the left, or to the last point because we have nothing to the right. So actually we can compute the moving average for a subset of our data starting from the radius here. So if we are using a radius 3, we have to start from index 3, which is the fourth point, and then going all the way to the end, except for the last points which correspond to the radius 2. So we have to skip the first 3 points and skip the last 3 points. In order to plot this correctly in the right place, we're going to use this function to create a set of x values so that we can align the two plots. And now we are going to compute the y values, the moving average. So for each index over this x value, we're going to start with the index equal to the radius and then going all the way to the end except for this number of elements. And then we're going to compute the mean from the index, the current index minus the radius, up to the current index plus the radius plus 1, because we're also counting the point, the central point here. And then we're going to return these two arrays, the x and the y. So if we test this, we call the function with these values 1, 2, 3, 4, 5, and we use a window of 1, we get this array for the x values and this array for the running average. So let's see what's happening here to make this easier to understand. So we have these 5 values here. These are our arguments, okay? And we have a window of 1. So since we have a window of 1, when we're looking at 2, we have to average these 3 elements. So the one before 2 and the one after 2. This means we cannot do the moving average on this first element because we have nothing to the left to do that. So this one gets taken out. So this would be index 0. This one gets taken out from the x vector here, which gives us the positions for which we have the moving average. We start with the position 1. Remember that Python starts indexing at 0, so position 1 is this element here. And for this element, we're going to compute the mean in this window. So it's the element and then plus and minus 1 because it's the radius of the window we're using. And this, the mean of these is this 2 here. Then we're going to shift and compute the mean over this, which is 3. And this is centered on the element of index 2. And then we're going to repeat for element of index 3, which is this one. This is the mean there. And we stop because we cannot go any further. We don't have values there to keep computing the mean. So this is the function that we create. We can set different values for the radius. We can send any array of values. Now we can use this to plot the daily excess mortality for 2020 when compared to the mean of all the previous years, and then plot a moving average with a window of 7. So the size of the window is 7 because we are using a radius of 3. It's the central element, the 3 elements before, and the 3 elements after. So this is the green line here, or we can do more, for example, a window or an 11-day moving average by using a radius of 5, and we have this red one here. So by adjusting this, you can increase or decrease the smoothing effect on your data. Note that we're going to lose some points at the beginning of the or the end because we are increasing the window. And this is one reason why in finance usually we use the n last points, because then we have the moving average all the way to the end. Usually the very old points are not that interesting, and the more recent ones are more interesting. Note that this is a simple average, so we are taking all the points with the same weight. There are lots of variants where you can have linear decay, exponential, and so on, where you give different weights to different points depending on the distance. And we're going to see something similar to that when we look at kernel density estimation and that kind of approach. But for this lecture, we're only going to do this simple moving average. So let's look also at COVID-19 data. You can get this from Direção-Geral de Saúde, but actually they submit a PDF report every day, so it's a bit of a nuisance to extract the data from there, especially because they keep changing the format of the report, and it's a PDF generated from a PowerPoint presentation, and it's quite messy. But I wrote some scripts to do that, and in this TXT file we have the data from May 2nd to September 12th. And we have 4 columns here. The first one are the total number of detected COVID cases, so those that were confirmed to be infected. The second one is the number of people hospitalized in each day. The third one is the number of people in intensive care units in each day. And the last column is the total number of deaths. So again, we can load the data, we can check the shape. The number of rows is the same. It's the same set of days, but now we have 4 columns instead of 12 like we had with the mortality for every year. We can also plot the data. We just plot the metrics because our series are in columns, and we create the legend with the this is hospitalized. We create the legend with those that were confirmed infected, hospitalized, and so on. The problem here is that the cumulative number of infected is so much that everything else in the plot gets scrunched down there, and we don't see it very well. So we can just omit the first column. So we're going to plot all the rows, and starting from the second column, so we omit the total number of infected, and we get something that now we can see. So these are hospitalizations, number of people in ICU, and the total number of deaths. So there is a difference between these series in that hospitalizations and intensive care units, it can go up and down, so depending on how many people come in and go out of the hospital, whereas death is a total count, so it always goes up. And this makes a difference when you're trying to compare data series, time series, because usually it's best to work with stationary time series. There are some more formal definitions of this concept, especially when you consider time series to result from a stochastic process with some parameters. But the informal idea is that a time series, the distribution of values does not change much over time. So it can go up, it can go down, it can be more or less higher, lower, and so on, but it has no clear trend. Now here, maybe hospitalization is not exactly stationary, but we can clearly see that death and total number of deaths and total number of infected people is not stationary because we're always increasing, we're always adding values there. So often you should convert the data into a stationary time series to help analysis. In these cases, we can, for example, consider the number of new cases or number of new deaths per day, because this should go up and down and not have this clear trend as the cumulative number has. You can do other things. If you have some model of what the process here, you can remove the trend. For example, do a linear regression, exponential regression, something like that. Remove that and retain the residuals, for example. But in many cases, we should transform our time series into a stationary time series in order to allow us to do some comparisons. Otherwise, if you include this trend, you can get strange results and things that are not really meaningful. So let's create a function to convert the total, this cumulative count of infected and death into new cases per day. So this function receives an array of values, a unidimensional array of values, and creates a new array where we have the daily change. So how many new cases we got per day. We're going to start with an array of zeros with the same size as the input array. So to compute this, we're going to compute for each day the difference between that day and the previous one. So for the first day, we don't have any previous value, so we'll assume the difference to be 0. That is implicitly assuming that the value on the first day is the same as the value before our time series begins. So we start with an array of zeros for our daily values, and now we fill in all starting from the second one to the end with the difference between those values starting from the second day to the end, subtracting the values starting from the first day up to the one before last. So we are shifting this one with respect to that one day back, and we are computing the difference between these. So, for example, I can illustrate this. Suppose we had this one for example, like this, 5, 2, 4, 10. If we subtract from these here these, so for example, doing this shift, we cannot get a value for the 1 because there is nothing to subtract from that. So we create our new array with the differences as 0. So we are assuming that before this 1 there was another 1 previously, but we don't have it. Now for this 4 we are going to subtract the 1, which is here, and we get a 3. From this 5 we're going to subtract the 4, we get a 1, and so on. And then at the end this one is left out. So this is what we're doing here. We're taking the values counting from the second, so these here, and we are subtracting the array of values up to the one before last, which is this one. And then we get all these differences. Because of this thing here, where we start with the zeros and we leave a 0 at first, this array now has the same size as the original one, which is a good idea, because then for plotting and comparison and so on, it simplifies things. So this function we can use now to get the values per day, both for the confirmed infected cases. We use the first column of our matrix, and the death. The deaths are in the last column of our matrix, but we send the last column here, we get the values per day, and these are the number of deaths per day. And now we can do the comparison here. So these are the newly infected per day. These are the hospitalized patients in ICU and the number of deaths per day. And now all of these are values that go up, they go down, but they don't have necessarily a fixed trend like they would if we were just adding new values. So here, one problem with the newly infected per day is that it goes up and down very much, and this is a bit noisy. So we can go use our previous function. We use a radius of 3, so a radius of 3 gives us a window of 7, and this is a week. We are going to compute a weekly moving average, and we get this moving average for the infected ones. We get this x value here, so we can overlap the plot in the correct place. And now we're going to plot the actual values, the daily values, as a dot here. And then we're going to superimpose here the moving average for these daily infected values. But this requires a few tricks, because now we want to put this on a label where we have infected and moving average, but as a single series, because this is actually a single series. We're just representing the data and the trend, the moving average there. So to do this, instead of using this method here where we create a legend and just give a label for each of the series, we're going to label each series individually. The reason for this is that we can omit the label on the points, and so we don't have the points as a separate series in the legend. We just have a label for the line. The other trick that we need to do is, because each time we do a plot, PyPlot changes the colors. When we start by plotting this series of points, and then we reset the cycle for the colors. So we call this GCA's get current axis. We get this axis part here, which is the object that is doing the drawing here in the figure, and we do set prop cycle, which is, these are the cycle of properties for automatically changing from one series to the other. We change a none, so you don't change the cycle, but it resets the cycle. This means that now the line with the moving average will have the same color as the points we put in the first plot there. So this is an example of a trick that you can use if you want to do this sort of thing. If you have something more complicated, for example, if we had several series that had these dots and the line with the same color, then it would be simpler to specify the color. In this case, this is just a shortcut to reset the cycle and not having to worry about the colors, letting PyPlot choose them automatically. Also, remember that if you don't add a label, if you don't add labels here and you don't add a label to a series, then that series will not appear on the legend, and only the series with labels will appear on the legend. So this is another way you can use to control which ones appear on the legend. So here we have hospitalization, we have ICU, we have the daily new cases infected, and the daily new death. So if we compare the daily deaths from COVID-19 with the excess mortality relative to previous years, we have this plot here. So we see there seems to be some correlation. There are some peaks here, some peaks here, but there's a lot more people dying relative to previous years than the actual confirmed death by COVID-19. So why this is happening, we cannot say from the data. There are many possible causes. Maybe there are deaths from COVID that are not being confirmed. Maybe too much emphasis on dealing with COVID has left other people dying from other causes. Or maybe this is just by chance. This may be a bad year overall, it seems to be. But in any case, what we can see from the data is that there is a very large discrepancy between the confirmed death of COVID and the excess mortality that is happening this year with respect to the average of the previous years. We can do this also. We can do it with daily mortality, but we can also use our function to compute the moving averages for the excess mortality in 2020 and the daily death confirmed by COVID. So this is just to illustrate the usefulness of creating functions, because once you create a function, you have a tool that you can reuse to quickly do something again and again without having to copy and rewrite the code. So in this way, we can smooth things easily into weekly moving averages. Okay, another thing that we can look at a bit more quantitatively are correlations. So we can see here that infections rise, infections per day have risen here, lowered and then risen again, and we can see the same thing here in hospitalizations. In this part, it's different because we're coming from the first wave. So hospitalizations were very high and people were getting better and going out or dying, some of them. But from this on, we see some correlation here. We also see a strong correlation between hospitalizations and internal people hospitalized in internal care units and so on. But correlation is something that we can actually measure and not just look visually. So we're going to do that. We're going to use the Pearson correlation coefficient, which is the covariance between two sets of data divided by the product of the standard deviations of each of them. You can compute this with NumPy, with this corcof function. That returns a matrix with the correlation coefficients of this series with itself, this one with the second one with itself, and so on. So, so this is the result from running this function. You get a matrix like this. So actually, we don't want the whole matrix. We just want the coefficient correlation value, which is the value either here in the first row, second column, or in the second row, first column. Because the one in the diagonal is always one. It's each series with itself. So we can do it like this. We can, from the result of the correlation coefficient, this is a matrix. We want the cell in the first row, second column, and this gives us the correlation coefficient. So when we compare hospitalizations with intensive care units, we see that the correlation is very high, 0.96 between these two. So hospitalizations and ICU. There is a glitch there. Probably I forgot to call figure, but it's this one, the green and the red in this case. We can also try to do this between the number of infected per day and the number of hospitalizations. But in this case, we get something that is very close to zero, because this one goes up when this one is coming down, and then this one starts going down and the other one, and so on, and the correlation is very bad. However, if we consider the periods starting from day 40 onwards, then there seems to be some correlation here. So the results of the first wave have already passed, and now we can look at the beginning of what probably will be the second wave. So we can do this. We can do this for the whole period, either with the original data or with the moving average, but the correlation coefficient is very low. But we can look at the period starting from day 40. So in this case, we get a higher correlation, not very high, 0.25, but it's a bit higher. And we see that these lines seem to be trending approximately in parallel, although with some delay, with some shift one relative to the other. So this is something that we can use correlations to find. We can try to see what the shift would be that would maximize the correlation between these series. So is there a delay, for example, between increase in the number of detected cases and increase in hospitalization, or between hospitalization and intensive care, or between intensive care and deaths? Can we improve the correlation between the series if we shift one relative to the other? So to answer that, let's create a function that does precisely this. So first we're going to select data from day 40 onwards. So this is the selected infected per day, the selected hospitalization, ICU. We're also going to create an X value here, so we can plot our data like this. Instead of starting at 0, we start at 40, because we need to remember that this is we threw away the first part of our data. And now we're going to create a function to detect this time-shifted correlation, or to measure the time-shifted correlation. We receive two sets of values. One we'll be considering to be the reference, and the other one is shifted forward relative to the reference. And it's going to be shifted by 0, 1, 2, and so on, up to some maximum value. So we start with an empty list for all our correlations, and we create a loop where we iterate through the shift. So shift starts at 0, then 1, and so on, until it reaches max shift. So in the range function here, we put max shift plus 1 so that we stop at max shift. Now what we do is we compute the correlation coefficient between the reference values starting at shift. So shift is first 0. This means all the reference values. But when shift is 1, we start with the second reference value and so forth, because we are moving forward along this reference. And we compare those with the other set of values, the one that we're going to shift, which will be pruned at the end. So we'll start from the beginning of this one and we'll remove some values at the end. So basically you can imagine that if you have a set of values here, and then you have another set of values here, we start by computing the correlation like this, which is a shift of 0. And then when we have a shift of 1, we are doing this. We are skipping this first one from the reference, and we are skipping the last one from the shifted, and we are only computing the correlation between these. And then we shift 2, we do it like this, and so on. So we get a list of the correlation coefficients of our data series shifted gradually by some values. And this is what we can do if we compare the hospitalization with the detected infections. So what we are doing is moving forward the daily new infections. So we are moving this series in this direction, and then computing the correlation to the hospitalization. And we see that correlation starts to improve and it peaks at 12 days. This means that if we shift forward the daily infection by 12 days, we optimize the overlap with hospitalizations, and the correlation is quite high, 0.7. So you can see the plot here. We can plot the newly infected ones, removing the last 12 because they go out of the plot, and we plot the hospitalization removing the first 12 here, so you get them lined up with this 12-day shift, and we can see that now the trends parallel. So by doing this correlation with time shifts, we can try to figure out the relation between two time series, how they fit together well. And this suggests that in general hospitalizations start to increase 12 days after detecting new cases. So we seem to be detecting cases with some 12 days before people start getting actually sick with symptoms and so on. So when we compare ICU with hospitalization, so we move intensive care units forward relative to hospitalization, we get something like this. So correlation is best when they are exactly on the same day, but then correlation starts to decrease. This suggests that intensive care unit patients may be coming directly when they are hospitalized. So it's often the case that they go directly to intensive care and they do not spend significant time out of intensive care before going there. Of course, this starts getting a bit tricky because now with intensive care we have around 30 per day, and this gets a bit noisier, and that's especially the case when we compare intensive care with death, because daily deaths are around 5 and we have lots of stochastic effects here. So this suggests that there is about a 2-day delay between intensive care unit and death, but this may be just noise, because we are dealing now with very small numbers, and the correlations here may not be meaningful. But this is just to get you an idea of what you can do to compare time series by shifting them relative to one another and computing the correlations. You can also do autocorrelation. So let's take infected per day and compute the correlations with shift with the series itself. If we look at the infected per day series, we can see that it goes up and down. If this is a periodic phenomenon, so it's always the same frequency, then we can, if we shift it by the right amount, the correlation will increase again. And in fact, this is what we see here. We see that as we start shifting the infected per day relative to itself, correlation goes down, but then it starts going up and it peaks again at 7, which corresponds to a week. So this happens because in the weekend there are less labs working, so fewer labs working, so there are fewer samples being processed, and then the backlog catches up during the first part of the next week, and we have these oscillations. And we can detect this by doing this autocorrelation. So shifting the time series relative to itself and checking to see if the correlation has peaks. So one important thing to remember when you're dealing, especially using libraries for cross-correlation, note that these things we did here by actually implementing the code is mostly for pedagogical purposes. So to help you understand what is happening there. Typically, you will not be implementing this, but just use something from the library. I'm going to show you one example. But you have to be careful because in signal processing, usually what they call correlation is just a covariance at different shifts. So it's the product of the function and the other function shifted by some value. Note that this is true for real numbers. This is actually the complex conjugate of the value, but if you are using real numbers, it makes no difference. And in any case, it's not the goal of this course to go too deep into these details. But this is important to know because if you do this with some data series, you get very strange results. You should always, when you use these libraries, if they use this kind of functions, you must use zero mean vectors. That means that you have to subtract the mean in order to get meaningful results. So always be careful what correlation means, because the Pearson correlation coefficient is different from these covariances that usually are computed, but in signal processing these are generally called correlations too, so be careful with that. In practice, this means that you can use some of these correlations and cross-correlation functions from library. For example, PyPlot has this autocorrelation function that does what we did here, but even better because it shifts both positive and negative. So you have here, this is what happens when we shift the daily infected positive, so forwards or backwards. But you need to be careful and give this to this function a zero mean vector. So since this is not centered at the mean, we need to subtract the mean from it. And now we get this graph, which shows a peak here at 0 because the series correlates perfectly with itself. But when we start shifting forwards or backwards, we have this peak at -7 and 7, which corresponds to that weekly oscillation. So this is ACOR for autocorrelation, and we also have cross-correlation, XCOR. For example, we have the hospitalization and the infected, newly infected here. Remember to subtract the mean, otherwise this will give you just a pyramid with no particular meaning. And we can also change this max lags argument. So by default, this considers a shift of minus and plus 10. If we change this, we can add more. For example, max lags 20 to do 20. And here we see that as we shift the daily infections forward, we have a peak here at 12, the one we found before. If we shift it backwards, then correlation goes down and it becomes even negative. So basically we can see that we can have the optimum correlation between the daily infected rate and hospitalization if we shift forwards by 12 days the daily infected rate. So basically, if the daily infected cases increase, we can expect that 12 days later hospitalizations will increase, and at the same time internal care unit patients will also increase because they seem to be synchronized. So to sum up, we saw in this case univariate time series, so it's the same one feature, vectors of data, but now the data are ordered because they come in a temporal sequence. This makes it meaningful to do things like moving averages, correlations, and so on. And we can also time shift the correlations to try to see if one of the series, or even the series itself, has some relation to some shifted variant of the other. This allows us to find, for example, delays in some processes or periodic events when we are comparing the same series. So in the case of autocorrelation. Note that statistics of time series is a lot more complex than I've been handling here. I just use Pearson's correlation coefficient by default, but this is just a basic idea. If you really need to do some serious work on time series, I would advise you to look at the statistics behind this and the assumptions when we are modeling time series. But for this course, we are just taking an overview of these different types of data, so we are not going to go deep into that. So that's all for now. I will have today, I'll put online the PDF with the exercises, hopefully by this afternoon, so sorry about the delay, and tomorrow we can talk about this in our meeting.